let's extend what we've done in 2 dimensions here to think about what a 3-dimensional vector might look like. I'm going to plot these by hand, and then I'm going to pull up, follow this link. That's kind of a fun 3D grapher, and we'll see these examples with a computer drawing them. But how I would illustrate these on paper would be something like this. The standard axes that we draw in 3 dimensions is usually written like this. So 2, and then an axis coming through. And by convention, it's usually this is the positive x-axis, here's the positive y, and positive z goes up and down. Is usually the standard. So if I want to illustrate some vectors, if I want to illustrate, or at least these coordinates, 0, 2, 0, that means I'm going to go nowhere along the x-axis, 2 along the y-axis, and nowhere up and down. So I think this point P, or point A, would be located right here. I think if I draw similar axes, then at the point 3, 0, 2, I'm going to go 1, 2, 3 along the x-axis, nowhere along the y, but 2 up. So 3, left and right 0, and up 2. And I think I would go 3 and up 2. And lastly, let's see if I can draw this. -1, 2, 3. So -1 on the x-axis would be back 1. I'm going to go 2 along the y-axis. So back 1, over 2, and then I'm going to go up 3. So back 1, over 2, and up 1, 2, 3. I think it would be something like this. Again, it's representing 3 dimensions on a 2-dimensional plane is pretty difficult, but I think these aren't bad sketches of what they might look like. I'm going to pull up this computer graphing tool here, and we're going to look at these 3 points with a computer graphing them. There are a lot of 3D graphing tools out there for you to use. This is the one that I've linked on the notes. It's kind of fun. You can manipulate the graph, the axes here. It's kind of difficult to do with a mouse, so I'm going to try not to move the axes around too much. But we can adjust the X, Y, and Z however we want here with the sliders, and the point will follow in tandem. So if we look at those points that we just graphed by hand, the point 0, 2, 0 will be 0 in the X, 2 to the 2 in the Y direction, and nowhere up. You note that this point just kind of slides along the Y-axis. Similarly, if we reset here in the point 3, 0, 2, again, down the x-axis and then up 2. Kind of fun. And maybe, I think we can even turn on a tracer here. Yeah, there you go. You kind of see in space how this thing moves. It's kind of nifty. And how about we try this again with the last one. So I'll turn the tracer on just so we can see it. And the last point C was at -1, 2, and then 3. So again, you kind of see it move back, then over, and then up. We end up at this point here. Let's apply and extend some of those properties from 2-dimensional vectors into 3D. I'd like to know how to calculate the length of a 3D vector, and also how to find the vector between 2 points in space. Before I write down the formula, I'd like to kind of figure out what the formula should be. And to do that, I'm going to think of how do I get from, say, a point from like the origin. I'm going to draw a picture. How about from the origin, which is at 0, 0, 0, to some random point in 3D space. I'm going to say it's like in the first, it's called octant, but it doesn't really matter. But I'm going to say it's like, say over here, at X, Y, and Z. So how do I get from here to there in 3D space? So note that in order to do that, I'd like to know something about. I'd like a coordinate grid. In order to do that, I'm going to try to draw a picture here. So to get from 0, 0 to x, y, z, I need to move some distance along an x direction. I'm going to need to move some distance to get, say, underneath of it in the y direction. And then I need to go up in order to get to it in the z direction. And if you imagine what we just made here, I think you can think of this as like we've actually built kind of like this is kind of like following like the diagonal of a cube, or let's call it a rectangular prism. So in order to get from, and what we're doing is trying to move from corner to opposite corner in this picture by following an x distance, a y distance, and a z distance. And what we're really finding to find the magnitude of a vector that goes from the origin to this point is really we're finding the length of like this diagonal of this cube. So how could we do that? I think one thing you could try to do is I'm going to try to split this up into something a little bit more manageable. I think what I'm going to try to do is maybe I'm going to do this in 2 steps. I'm going to try to find the distance or a vector that takes me from the origin to a point that's directly underneath of this vector. And then what I'll have is, if you can visualize this, I'm going to create a triangle with sides of this length that's down on the plane here, this leg that goes straight up, and then the distance will end up being this thing I'm after. This distance will be this vector that goes from the origin up to xy. And note, since I'm going to be I'm directly under it, that this is going to be a right angle. So if I could figure out what this length is, then I'd have a right triangle, and I could use Pythagorean theorem. So I think what this amounts to is I'm actually going to use Pythagorean theorem twice. I'm going to find this, what's called this projection, or this length that's on the bottom here. In order to find this blue length, and I don't have a good symbol for this, but I want to find this length here. And I think by the Pythagorean theorem, that length is x squared plus y squared. This length is one side of a right triangle. And maybe I'll try drawing this triangle flat like. This length is x squared plus y squared. This length is z. And this resultant is the vector I'm after. This is the magnitude of the vector I'm after. So what is this length? Well, here's a right triangle. Pythagorean theorem applies. D squared is equal to a squared plus b squared. Squaring a square root undoes it, so the distance squared is really equal to x squared plus y squared plus z squared. Therefore, the distance is the square root of this. Long story short, the distance in 3 dimensions is the Pythagorean theorem, just with 3 terms instead of 2. So we say that the magnitude of a 3D vector is the square root of the x component squared plus the y component squared plus the z component squared. Similarly, similar to the vector between 2 points, so that we saw in the two-dimensional case, if I want to know if I have between 2 points, say A and B, the vector from A to B is B minus A. Or if you're in components, that would be B1 minus A1, B2 minus A2, B3 minus A3, if we're in 3 dimensions. So analogs from 2D to 3D are very, very similar. Just since there's an extra dimension, there's an extra term in each of these two representations. So we can do things like finding the vectors between some points. We can find the lengths, and we can even find things about some special things like three-dimensional shapes like parallelograms. So P is at this coordinate, Q is at this coordinate, and we want to know what a few of these vectors are. From O to P, O is always the origin. This would be terminal minus initial, which would be the x component would be P minus O, P minus O, P minus O, -3, 1, 2. Which, not coincidentally, from the origin to a point is the position vector is just the coordinates in component form. If I want to find the vector from P to Q, P to Q, that's terminal minus initial, so Q's components minus P's components. So Q minus P, Q minus P, Q minus P. 4, -2, 1. And lastly, if we want to find the length of vector PQ, the length of this vector that's the length of 4, -2, 1. And our distance, the length function is just the Pythagorean theorem, just with all three of these terms. So that would be the square root of 4 squared plus -2 squared plus 1 squared, which is 16 plus 4 plus 1, which is the square root of 21. Lastly, we'd like to, here's a description of 3 coordinates of a 3-dimensional parallelogram. And we'd like to know, and what we want to know is how to find this this missing coordinate C. Important things to note about however you if you draw a parallelogram, I'm going to draw just a generic one. Some things that are important about parallelograms. First of all, when it's labeled in this fashion, the coordinates start at any vertex and go around either clockwise or counterclockwise in this order. So I could do A, B, C, D. What I would not do is A, B, C, D, because then I could not go around the parallelogram in this order. Also, opposite sides are parallel. And also opposite sides are the same length. So it looks like in this picture, something I know about this is that I know that length side AB is parallel to CD. And also the length of AB is the same as the length of CD. Or maybe even better yet, straight up, this vector from AB is the same as the vector from A to B, same as the vector from D to C, because they're parallel and the same length. So if I could write a vector, if I could find the vector form of AB, I could write that as the vector form of DC, and then I could equate the two vectors component by component. AB, because of the 2 points, I know that AB is B minus A, so 2 minus -1, 0 minus 2, and -1 minus 1. which is 3, -2, -2. DC is terminal minus initial. It's going to be C minus D. I don't know what the coordinates of C are, so I'll leave them, how about as X, Y, and Z. And I'll subtract the coordinate, subtract C from each, D from each of those. So terminal minus initial, so C minus D, C minus D, C minus D. Since these two vectors are equal, then their component forms are equal. So that tells me that 3, -2, -2 is the same as x minus 3, y minus 1, and z minus 4. And if these are equal, then each of their component y's are the same. So I know that x minus 3 equals 3. I know that y minus 1 equals -2. I know that z minus 4 equals -2. Therefore, x equals 6, y equals -1, and z equals